This is the coldest place on the planet, and possibly the universe. It's 40 times colder than space. But why? That's because this cosmic freezer stores the world's most advanced quantum chip. To make it work, Microsoft had to invent a new state of matter. Let that sink in. Microsoft, the company that made Windows XP, currently changed the laws of physics. Solid, liquid, and gas just got a step cousin, and it's called Majorana 1. This could break the computing world. And to understand it, let's look at it as a 5-piece puzzle that starts with Majerana 1, a new state of matter. Majerana 1 is a quantum chip that relies on an entirely new state of matter to work correctly. That is not just big for the world of computers, technology, and quantum computers. It's a ground-shattering discovery that still rocks the physics world, and it came from one of the Microsoft labs. Based on everything I've read, here's how the chip seems to be working, in simple terms. Imagine you have a secret message written on 2 pieces of paper. Each piece by itself looks like random gibberish, but when you put them together, the full message appears. Now here's the weird part. If you move or swap the pieces in a special way, the meaning of the message can change completely. Majerana 1 is like that. It's a particle that isn't whole on its own. Instead, it exists as 2 linked halves that only make sense together. But unlike normal particles, swapping these halves actually changes the system in a unique way. This strange behavior is why scientists think Majerana particles could be useful for quantum computers. They can store and process information in a way that's naturally protected from errors. Majerana 1, or the Majerana 0 mode, is this super weird kind of quasi-particle that scientists think exists in certain topological superconductors. It's named after Ettore Majorana, who, back in 1937, predicted the existence of particles that are their own antiparticles. That's already pretty strange, but what's even crazier is that in solid-state systems, these Majerana 0 modes behave in a way that doesn't fit into the usual rules of quantum mechanics. So how does it actually work? Imagine you take a tiny nanowire and smash that like button, just like you should, if you haven't done so already. But no, in all seriousness, imagine taking a tiny nanowire and putting it in contact with a superconductor. If the conditions are just right, meaning the material has strong spin-orbit coupling and you apply a magnetic field, this system can enter a new state of matter, topological superconductivity. And when that happens, something remarkable appears at the ends of the nanowire, a pair of Majerana 0 modes. These modes are like 2 halves of an electron, spread apart yet mysteriously connected. Now here's where things get really wild. Normally, particles follow either fermionic, like electrons, or bosonic, like photons, behavior. But Majerana 0 modes don't do either. Instead, they follow something called non-abelian statistics, which means that if you take 2 of them and swap their positions, the entire quantum state of the system changes in a way that depends on the order in which you did it. This isn't just a small detail. It's an entirely new way for quantum systems to behave. This is why scientists are so excited about them for quantum computing. Right now, quantum computers struggle because their qubits are fragile. Tiny disturbances can mess up their calculations, but qubits built from Majerana 0 modes would be naturally protected against these errors. They store quantum information in a way that isn't easily disturbed, making them a potential breakthrough for building stable, fault-tolerant quantum computers. This is the first part of a 5-part puzzle. The second is about how Microsoft managed to fit this technology into their chip. Let's talk about the hardware of Microsoft's Majerana 1 chip in a way that makes sense without getting lost in heavy physics jargon. Imagine you're building a super secure vault for storing information. Regular vaults, classical computers, use simple locks, while quantum computers use super fragile locks, qubits, that break easily when disturbed. Microsoft's solution is to build a self-protecting lock, something that naturally resists tampering. This is what the Majerana 1 chip is designed to do. At its core, this chip is made of a special kind of material called a topoconductor. It's a mix of indium arsenide, which is a semiconductor that helps control electrons in a precise way, and aluminum, which acts as a superconductor, meaning it allows electrons to flow without resistance. By combining these 2 materials, the chip creates a perfect environment where something strange and powerful happens. Majerana 0 modes appear at the ends of tiny nanowires. These exotic particles act as 2 halves of a single electron, but here's the cool part. If you move them around in a special way, they don't just switch places, they change the entire state of the quantum system. This is called braiding, and it's how Microsoft plans to store and process quantum information with incredible stability. Right now, companies like IBM and Google use superconducting qubits, which are like delicate snowflakes. One wrong move, and they break. Microsoft's topological qubits, built using Majerana 0 modes, are way more stable because they naturally resist errors. Instead of needing thousands of error-correcting qubits to keep a single logical qubit stable, like traditional quantum computers, Microsoft's approach requires far fewer. But that still doesn't solve the error correction problem quantum computers are famous for. One of the biggest challenges in quantum computing today is error correction. Classical bits in a computer are either 0 or 1, but quantum bits, qubits, exist in a superposition of both. However, qubits are highly sensitive to environmental noise, causing errors in calculations. But topological qubits are superior. That's because Microsoft's Majorana-based qubits have an advantage over traditional superconducting qubits used by IBM and Google in error correction, longer coherence times, and scalability. The one problem companies couldn't solve. Topological qubits are immune to small disturbances since information is stored in a globally entangled state across two Majorana zero modes. The non-local nature of information storage means that noise, which typically affects quantum systems, doesn't easily disrupt computations. Traditional superconducting qubits require massive error correction overhead, meaning you need thousands of physical qubits for just one logical qubit. Microsoft's approach could allow them to build a quantum computer with far fewer qubits. And this brings us to the fourth piece of the puzzle, braiding. The real magic of Majorana qubits happens through braiding, which is how quantum information is processed in a topological system. Since Majorana's zero modes exist in pairs, swapping them, moving them around each other, performs a quantum computation. Unlike regular qubits, which require delicate microwave pulses to manipulate quantum states, Majorana qubits store and process information through geometric movement. This method is called adiabatic braiding and is what makes topological quantum computing unique. If two Majorana zero modes are swapped, their quantum state is altered in a predictable way. On top of that, these operations do not depend on time, unlike standard quantum gates, making them robust against errors. Not to mention, the more complex the braiding pattern, the more complex the computation. That's why Microsoft is developing specialized quantum circuits that will allow for this braiding to be done in a controlled way, forming the foundation of a functional topological quantum computer. And that brings us to the final piece of the puzzle, which is scalability. Microsoft's Majorana 1 chip is designed to solve one of the biggest hurdles in quantum computing, scalability. Right now, most quantum computers struggle to go beyond a few hundred qubits because they require massive error correction, complex wiring, and ultra-low temperatures. Microsoft's approach, using topological qubits, could sidestep many of these issues and allow them to scale to millions of qubits. This makes it possible to pack far more qubits onto a chip, because the qubits are naturally protected from environmental noise. Unlike the fragile superconducting qubits used by other companies, Microsoft's design is also more compact, requiring fewer control lines and less wiring, which is a huge advantage when scaling up to millions of qubits. Instead of cramming everything into one processor, Microsoft plans to connect multiple smaller quantum chips together, kind of like building a supercomputer with smaller, linked units. They can then use Azure Quantum, their cloud platform, to allow people to access these powerful quantum systems without needing their own hardware. This cloud-based approach lets Microsoft scale its quantum computing power over time, upgrading the backend without requiring users to change their software. With these innovations, Microsoft believes they can push quantum computing into practical use, solving problems classical computers can't, like simulating complex molecules or breaking current encryption methods. The goal is to make quantum computing available on a massive scale. Here's another video AI enthusiasts loved watching. This is AI Exposed, demystifying the world of artificial intelligence, one video at a time.